Hey everyone, today we are going to start the Generative Adversarial Network, or the GAN. So before we do an implementation, I always like to take a look at a little bit of the math that goes into it. Light prerequisite to this is that you already know what a variational autoencoder is, because there are some correlations between them, kind of where does this architecture come from. And so we're going to look at that connection in just a little bit. But first, let's remind ourselves a little bit about what exactly is a generative adversarial network. And there's the first term, generative. It's exactly what you think it is. The entire purpose is to create new data. And you see this in lots of fun forms, like generating images, generating audio, maybe even generating text, though GANs are not really used for that, at least in this case. But there's all sorts of applications of GANs that you can use. GANs have more or less fallen out of fashion as a standalone generative model today, just because of how good diffusion models have become. And so we're going to be looking at diffusion later, but the GAN loss, the entire GAN paradigm that we're going to be exploring, is still very relevant and acts as a crucial auxiliary loss to a lot of important models out there. One of them being the stable diffusion model and the VAE backbone. So again, we're going to be seeing a lot of this stuff as we start implementing things. But let's just start with the kind of prereq here of what was the variational autoencoder. The variational autoencoder is a model that takes data, compresses it down, right, using an encoder. We compress to some known latent space. It's a Gaussian latent space, and we use some type of Kale divergence term to constrain the latent space, so we actually get a roughly Gaussian space C. And then we have a decoder that takes some sample, it samples from this distribution, and then generates something, the decoder. And so that was it. That was the entire VAE paradigm, and the VAE had a reconstruction loss plus a KL divergence loss, and that loss was to ensure that the latent space was indeed Gaussian. Now, how is this connected to the GAN? The GAN actually has two parts to it. It has a generator and the discriminator, and this setup is what makes it adversarial training. And so we're going to see that in a bit. But first we start with some random noise here, right? Random noise called Z, and this random noise is typically Gaussian, right? We sample some standard Gaussian noise is what we use. We give it to the generator. Well, that looks a whole lot like this part right here, taking the random noise Z and passing it to our decoder. Because that's exactly what it is. In a variational autoencoder, once you've trained the VAE, you actually can do something cool. We know that the decoder is expecting some latent vector Z that's sampled from this Gaussian distribution. So that means I can just sample some Z and pass it to the decoder, and we're good to go. So that's the same as taking some noise from some known distribution, passing it to our decoder. And in this case, the generator is basically the decoder of our VAE. So that's step one. Take some noise, pass it to the generator, and it generates some fake data. We also have a collection of real data, right? We have our, let's say we're training on MNIST, right? So MNIST, right? We have some MNIST data, some image data. So we have a collection of real data as well. And then we have a discriminator, and this is the new part. And the discriminator's job is to identify which images are real and which images are fake. So we're going to give it some real data from our real database. We're going to give it some generated data, some fake data from our generated data. And the discriminator's goal is to identify which of these pictures are real and which of these pictures are fake. And because there's only two classes, as you see here, we can use the binary cross entropy loss, right? Because it's basically a binary classification problem. And so that's basically all we need. That's the setup. Now, how is this exactly trained? There's two parts. The discriminator's goal is to get really, really good at identifying real versus fake data. So this one's goal is to minimize, right? Minimize the BCE loss, just like that, right? We're going to minimize the BCE loss. The generator, on the other hand, has to generate data that's so good that the discriminator is unable to differentiate between the two classes. And so this one's goal is to maximize the same BCE loss, because the generator is trained to fool the discriminator. We want to update the generator in the direction that goes against the discriminator. And this is what makes it adversarial, because the discriminator's goal is to be able to identify real and fake data, and the generator's goal is to create fake data that's so good that the discriminator is unable to identify the difference between the two. And so this is the clear setup for the for the GAN, right? That's what makes it adversarial. Now, this does lead to some training instability. GANs on their own are not perfect. And so we're going to be looking at a bunch of variants of the GAN kind of going into future videos. But for today, we're just going to look at the most basic one. And so the entire thing is basically handled by this single loss, the BCE loss. The discriminator's goal is to minimize the BCE loss because we want it to get better and better at identifying the differences between real and fake data. And the generator's goal is to maximize the BCE loss because we want to make sure that the generator is making the discriminator more unsuccessful at classifying. And if the discriminator is getting worse, that means the BCE loss is increasing. And that's basically the simplest way to understand exactly what's going on. And so what we're going to do is we can see this entire implementation, right? All the math will hinge on this BCE loss. So that seems like a good starting point for us to kind of just, do a little bit of this derivation. If you are unsure about the BCE loss, I believe in the very first video, we actually derived the binary cross entropy loss. So I'm not going to do that here today, but the BCE loss is essentially just a maximum likelihood estimate if you do the logistic regression derivation. So, but the BCE loss looks a little bit like this. The loss between the cross entropy basically between our y, the true label, and y hat, our predicted label, is just going to be -1/n. We'll have a sum because it's an average, and then it'll be a y log y hat plus 1 minus y log 1 minus y hat, right? So again, if you don't know where this comes from, I'd recommend looking at that first video or just looking it up online because it's important to know where this comes from. But this is our binary cross entropy loss. And so what we're going to do is break this into two problems. We're going to break it into the real images and the fake images. So what we're going to do is, what is the loss h for real images specifically? So this is when y is equal to 1. So it's a binary classification problem. So I'm going to say that 0 is fake and 1 is real. That's arbitrary. We could have also made 0 real and 1 fake. It doesn't make a difference. It would just flip stuff in the math. But other than that, it wouldn't make any meaningful change. So we're going to set y as 1 for real and y hat, right? What would this look like? Well, if y is 1, that means this y term is 1. And this 1 minus y term is 1 minus 1, or 0. That means this entire term disappears, and we're just left with 1 times log y hat. Okay, so let's go ahead and do that. That's going to be just the -1/n sum y times log y hat, but y is just 1, so it's just 1 times log y hat, so it's just log y hat. Simple as that. And then similarly, the fake images, y equals 0, and y hat is going to be, again, -1/n sum. And if y is 0, that means this term disappears, right? That'll go away. But 1 minus 0 is just 1, so it's just 1 times log 1 minus y hat, which is just log 1 minus y hat. So it's going to be log 1 minus y hat. And now here's the important part to keep in mind. What is y hat when we're looking at a real image, and what is it when we're looking at a fake image? And so y hat, let's do y hat real, right? Real y hat, assuming we're passing in a real image. That means it's coming from real data. Let's call that x. Real data x is being passed to our discriminator, because the discriminator is the thing that produces y hat, right? It's the y hat is the prediction of the discriminator. So that means this is just dx. Simple as that, right? So our prediction is just x because we're passing in x, our real image. On the other hand, what is y hat for our fake images? Well, that's just d of our fake data. And remember, fake data is generated by gz. So that means it's going to be gz, just like that. So this is what it would be when we're passing in real data. This is what it would be when we're passing in fake data, because gz is the generative model creating our fake data, and the discriminator is just discriminating between x and our gz, right? That's our kind of end goal. So we can just plug those things in. That means this will be -1/n sum log, and instead of just y hat, we're going to write dx. And this one's going to be -1/n sum log, and instead of 1 minus y hat, it's going to be 1 minus dgz. right? And that's the kind of simplest way we can write this, where this is assuming it's a fake image. So the discriminator is getting the generated fake image, dz, and this is assuming it's a real image. So the discriminator is getting the real image x, and that's it. And so this on its own is kind of setting it up. So we can then write our final loss is just the sum of the real and the fake. So it's going to be -1/n. It's going to be a sum. And then we're going to throw a log of dx in there plus, and then we have the second log of 1 minus dgc, just like that. So that's essentially our entire setup for this problem. Now, there's a couple of little details that are lost because we assumed that if we assume that y is just some binary variable, 0, 1, because we one-hot encode our data, right? It's either real, it's either fake, or it's real. Can't really be both. But if we treat y kind of like a distribution, then some more information can be achieved, right? We can actually see a little bit more. So let's go ahead and do it that way. Let's create some dummy variables. Let's say px of x is the distribution, right? Distribution of the real data x. So this is what we're trying to model, right? The real data, the distribution of the real data. Then we're also going to create a pz. This is the distribution of noise, right? So in our case, we know this is going to be standard Gaussian because that's what we normally use. So yeah, this is going to be the distribution of the noise data. And so let's go ahead and just rewrite a couple things. Here we said that y is actually just 1, or y is equal to 0. But instead of just y being some one-hot encoded vector, or one-hot encoded value of 0 or 1, why not just make them distributions, right? So let's write it this way. Let's write hreal between our px x. So this is y is going to be pxx. So basically y is what is the true data distribution? And we know it should be 100% real or 100% fake, right? So it's either 0 or 1. But just for argument's sake, let's say it's a distribution. There's some probability. So there we go. So we have pxx. And we want it with dx, right? This is our real data. So we want to do it with y hat equals dx. So there you go. So this is y, and this is y hat. And y hat comes from dx, and y will come from here. So this is the kind of predicted distribution, this is the true distribution of the data, which we again know is 1 or 0, 100% or 0%, depending on what you're doing. But let's just say it's some probability, right? Just for argument's sake. And again, we have y hat here, and we know because this is a real image, y hat is being produced by the discriminator on x, right? The true data x. So I haven't done anything here. I've just rewrote this. So instead of it always being 1, it's just some distribution, which we know is always 1. It's just for argument's sake. And so now that we have that, we can go ahead and write the continuous form of this of cross entropy. So if you don't remember, the cross entropy of two distributions is just the first thing. So it's going to be pxx times log of the second thing. In our case, it's going to be dx, just like that. And then we have a negative in front because this is our entropy formula. In the exact same way, we're going to do for fake images pz and dgz. So first of all, we have a slight difference here. This probability is over x, but this one's over our kind of selected noise distribution, our Gaussian noise distribution, and that's because the operand is actually z, right? So the operand of this is 0. So the way to think about this is this is modeling directly the data distribution. This is modeling the generated data distribution, but not directly. We're doing it through this latent variable z. We're going to simplify this a little bit later, but for now, let's just keep it this way, right? For now, this is fine. So this is going to be pzz, and then it's going to be log, and let's just kind of keep it. Everything else will be the same. 1 minus dg of Z, just like that. So this is our cross entropy. And again, this is a distribution over Z because this is kind of the argument of our function. We can simplify this, we will simplify this to be the, instead of doing the distribution over our kind of noise distribution Z, we're going to be doing it over the generated distribution, which we'll call PG a little bit later. But for now, this is fine. And so that means our final distribution, right? Our final HD, what is the entropy? Is just the sum of these two, just like we did before, right? The sum of the real and the fake. That's just the sum of these two things. And so we can just write negative integral, and this is going to be px. Just for simplicity, I'm going to ignore these extra arguments. So px log dx plus pz log 1 minus dgc, just like that. So that is our entropy. Now our goal is to minimize this entropy, right? We want to minimize this, okay? Instead of minimizing it, you can also write it this way. There's nothing wrong with this, but to keep it in terms of the notation that you'll probably see online, we, instead of saying we want to minimize the discriminator, we're going to say we want to maximize the negative of our discriminator, which is fair, right? Minimizing a function is the same as maximizing the negative of the function. So we're going to write our final loss, D. It's going to be the maximum, right? And we're going to maximize D. And we're going to write everything we had here, right? Nothing new. And so actually, let's do one more step real quick before we write that. We can actually simplify, or not simplify, but just rewrite this a little bit differently. Notice that if we have, as a recap again, if you don't remember, the expected value of f of x is equal to the integral of the probability of x times f of x over x, right? That's what it is. And so what do we have here? We have the probability of x times some function of x. And we have the probability of z times some function of z. And so these are just expectations, right? We can rewrite this as expected values. So let's just go ahead and do that just to keep it simple. So we're going to do equals negative expectation. And the first expectation is over p of x. So it's going to be x comes from our data distribution x. And it's the expectation of log d of x, just like that. And the second one, again, the negative will keep going. And so in the second one, this is going to be the expectation of z from p of z, and then log of 1 minus dg of z. Simple as that. So we just rewrote it in the expected value form rather than keeping the integrals. Just makes life a little bit simpler. And so we're good to go here. We have what we need. And so now we can go ahead and write our loss is going to be, we want to minimize this or maximize the negative of it. So we're going to maximize with respect to the discriminator, the expected value x px log dx plus expected value of z pz log 1 minus dg z, just like that. So this is set up. This is exactly the same as minimizing what we had before. So we're good to go. This is our loss. Now, to make this loss just a little bit more general, the thing is that we don't actually know when we pass our data, or at least the loss doesn't know. The label tells us, but the loss itself doesn't know. Is what we pass into the discriminator from x, the original data, or is it gz, our simulated, or our generated data? We're not entirely sure which one it is. And so just to make this a little bit more generic, we're going to use the same variable x here. So we're going to write LD is max d expectation. X comes from here. This is going to stay the same. dx plus the expectation. And actually, we're not going to write that just yet. We're going to get back to that. The expectation of log 1 minus d. I'm going to again write x here. Because again, we don't know if x is from the data or like what it's from. And here we're just going to write, just as simplification, we're going to write x is from the generated. So PG is the distribution of the generated data. That's PG. PX is the distribution of the real data. And that's it. That's the key idea. I just wanted to, it's just a light simplification that we're just going to keep for now, but it's not a big deal. So there we go. All right. So now that we have that's it. That's entirely our loss for the discriminator. That there's really not a lot going on. And our goal is to maximize this with respect to the discriminator. And that's it. What about the generator, right? So the next part. So our goal, if you remember, is to, the entire point of the generator is to minimize the discriminator's ability to distinguish between real and fake samples. And so what we're going to do here is we're going to use our discriminator and see how can we update the generator such that the discriminator gets worse. That's basically the entire game here. And so to do this, how we can do it, I'm going to do a little bit of it, and then the rest of the math is essentially identical to what we had done up here, so we can kind of skip over the repeated parts. But let's just write down again, y hat is going to be negative 1 over n sum, we'll do it in the discrete case again, y log y hat plus 1 minus y log 1 minus y hat. That's what we have. And so here's the key part. What we're going to do is we want to pass in y, or let's do y hat first. We know that we're passing in y hat to be fake data. So that means we're passing into the discriminator our fake generated data. But we want the label to be true. And that's the key idea. Let's kind of look back again. Here, we passed in, let's kind of keep going up a little bit. Here in fake data, or in the real data, we assumed that y hat was dx. It was real data x. And our label was 1 because it's real data, right? That's what the discriminator expects. So it's the same. We're passing in real data, and we predict it to be real data. And that's it. Right? That's pretty clear. The generator does exactly the opposite. We pass in fake data. So we're passing in our GZ, the simulated data, but we want y to be true. We want it to predict, not true, but 1. We want it to predict that it's real. And that's the key idea. We can see that there's a difference here because before we just passed in dx, or not px, sorry. Let's write that a little bit better, dx. Before we passed in real data x, and we said that it's real data. But the generator passes in fake data, but we want to say it's real data. And we want to update the generator such that we minimize this specific loss, right? Basically opposite of what the discriminator is trying to do. And this is what makes it adversarial training, right? So if we actually try this out, right, it'll look something like this. It'll be negative 1 over n. Y in this case is 1 because it's true. So that means we only keep this term. 1 minus 1 is 0. So this whole thing will go away. And if y is 1, then we're just left with log y hat, right? So it's going to be sum log y hat. And in our case, log y hat here is going to be dg of z. So it's going to be negative 1 over n sum. It's going to be log dg of z because it's generated data, right? Generated data. And one other kind of detail here is when we're updating the generator, right? When we're doing this generator step, we hold the discriminator constant. So we don't update the discriminator and the generator at the same time. We do them one at a time. And so that means we're going to just say this is d star, right? Like it's our current iteration or version of the discriminator. And so there we go. This is essentially our setup. We have our generator and we're trying to minimize this loss, and we're holding our discriminator constant to actually do all this. And so if we performed all the same steps that we did earlier, and we move to the continuous loss function, and then we convert it to expected value, we'll get exactly the same thing. We're going to get the loss of the generator, and this time it'll be a min. It'll be a min generator, because remember, our goal here earlier was to maximize this loss function with respect to the discriminator, because the loss function, the discriminator, wants to maximize the log probability of these things, of the two classes. And by maximizing the log probability, it's getting better and better at identifying real versus fake images. On the other hand, our generator wants to do exactly the opposite. It wants to minimize the log probability such that the discriminator is unable to distinguish between them. And so everything in our formula stays the same of the loss from before. It's just the loss for G is going to be a minimum instead, using with respect to G specifically, right? So it's going to be X. And for now, just to simplify a little bit, I'm going to call this, let's see, we called it px here. So yeah, let's just keep it the same for now. Px. And this is going to be log. And it's going to be log of d star, right? D star x. Because again, in this step here, when we're computing this loss, the loss is with respect to g, and we have a constant discriminator. We don't update the discriminator in this step. This is the generative step, or updating the generator step. So we're using the current iteration of d. It's not updatable. And then plus the expected value of x coming from the generated distribution, and again, log 1 minus d star x. And there we go, right? That's our setup. And so our final loss function, there's a couple of ways. You'll see this notation actually in a couple of different ways. Online, it's completely up to you how you write it, but you can clearly see that we have a min-max game here going on. And there's essentially, we do them one step at a time. So our final loss is going to be, we want to minimize with respect to g, and we want to maximize with respect to the discriminator. And we want to do this on the log of our discriminator x, right? Probabilities basically, plus log of the 1 minus discriminator of x, but let's just go ahead and write it as g of c. And there we go. This is essentially the loss function for our GAN. And that's it. It's as simple as that. So you could stop right here. So you have everything you need now to understand GANs. What we're going to do next is more of just like extra credit, right? Because I want to show the relationship between this and the Jensen Shannon Divergence. So it's a little bit, a little bit more advanced, but probably interesting for some people who are like more into the statistics of what's going on. So what I want to show is the relationship between what we just did here and the Jensen Shannon Divergence. So let's go ahead and do that. So again, if you don't want to see this part, none of this is really relevant. We won't implement it this way. We're going to use the standard form, but this is just kind of a nice to know rather than a need to know. So let's go ahead and do that. The question I want to ask is, what is the ideal discriminator? Basically, we want to find a form for d star x. We actually want to like solve for it. So let's just go ahead and do that. That should be pretty straightforward because we already had a form for the entire thing. So let's go ahead and write our loss discriminator. If you remember again, it was basically we want to maximize the discriminator of the expected value of x px log dx plus the expected value x pg log 1 minus dx. Right, that's all we had for the loss discriminator just earlier. So what we're going to do, let's just kind of write this again as the, let's just write this again. Instead of its expected values, just put the integrals back, or the sums, it doesn't matter. But this will be the integral of px, probability of x, of log dx, and this is x is over px, plus the integral, again, x over pg. This is going to be pg log 1 minus dx. Simple as that. And so we have everything we need here. And so what we want is to essentially take the derivative of this. So we have the loss of d. Well, what actually maximizes this? So take the derivative, set it equal to 0. To take this derivative, we can just kind of ignore the integrals. We don't really care about them. We just want the operands themselves. So what we want to do is dld divided by our, or not divided by, we're going to take the derivative of the loss with respect to our dx. And so we know that this is basically just px times log dx plus pg times log 1 minus dx. So we can go ahead and take that derivative pretty easily. The derivative, these logs are actually natural logs, so the derivative of natural log of x is 1 over x. So this ends up being px over dx plus pg over log 1 minus dx times, right, chain rule, so derivative of the inside is now, what's derivative of 1 minus dx with respect to dx? It's just minus 1, so times -1. And so our final thing will be px over dx minus pg over, or sorry, my bad, there shouldn't be a log there, it's just 1 minus dx. 1 minus dx. There we go. And we can just go ahead and set it equal to 0 and solve. And this is just simple algebra. So if you do it, you'll find that d, I'm going to call it d star x, right? Our ideal discriminator is going to be p, and instead of writing px, just so it's clear, I'm going to write p data, so pd, over pd plus pg. So that is our ideal discriminator. And this kind of makes sense because if our data is, if x is real, right? So these technically all have an x next to them, but I'm not going to write it over and over again, just to make it clear. If x is real, that means the probability of in our real data distribution should be close to 1. That means you'll end up with, and the probability in our generated data distribution would be close to 0. Right? So that means the numerator would be 1 over 1 plus 0, so this would be close to 1. And if x is generated, that means the numerator would be 0 and the denominator would be close to 1, so it'd be 0. And so we can see that this kind of makes sense, right? And our generator and the discriminator are fighting over making this, fighting over basically this ratio here. And so now that we have that, let's go ahead and see how this is connected to the Jensen Shannon divergence. And so to start this off, we just need to quickly think again about, or remind ourselves again about KL divergence. So if you don't remember, KL divergence is a very common metric to measure the distance. It's not really a distance, but either way, a distance between two distributions. If you have two distributions, P and Q, this is basically, you can rewrite it as the sum of P. So basically, we'll sum over I equals 1 to n. It's going to be over pxi times log pxi over qxi, just like that. And so this is your standard KL divergence. And again, this is the sum of basically some weights, which are probabilities, times a function, right? So this is again just an expectation over p, right, over a distribution p of log p x over qx, just like that. So a simple expected value. And so what you should start to realize here is that what did we write earlier? What we had is an expected value plus another expected value, right? And then when we continue to write it out, we start to get a little bit more information. So we're going to see how we get from this form to something that looks like this. So let's just keep going real quick. So first of all, we have solved for some ideal, right? Ideal d star x. So let's go ahead and plug in our ideal into our loss function. So to do that, we're going to do, let's see here. All right. So our LG, right? So let's go ahead and do that now. So our loss for the generator, remember, is minimizing with respect to the generator. The same function as before, right? The discriminator is maximizing this thing. Our generator is minimizing this thing. But other than that, it's the same thing. So it's going to be the expectation of x, px, and it's going to be log. And remember, this is going to be our d star, right? Some constant, whatever the current iteration or perfect version of our discriminator is, plus the expectation of, again, x, p, g, and again, log 1 minus d star x. Just like that. And we've solved for some expression for this d star x, so let's just go ahead and plug it in. Right? That's the easiest way to see what happens. And so that's going to be equal to min g, expectation, and it's going to be x, px, log. And so d star x is, as we had written, it's going to be pd over pd plus pg, just like that. And then other one's going to be expectation x from our generator distribution, and it's going to be log. it's going to be 1 minus, so it's going to be 1 minus the data over data plus g. So that's going to be data plus g minus data over data plus g. And this will cancel, so it's just g over d plus g. So it's going to be pg over p data plus pg, just like that. So that's our setup, right? That's basically our new loss function with our ideal, quote unquote ideal discriminator. And so now that we have that, we can start to see a little bit of correlation between what we're looking at. Notice our KL divergence here is the expectation of the log of two fractions, right? Well, isn't that what this looks like? The expectation of the log of two fractions, and another expectation of the log of two fractions. And the other connection you can make is this actually looks a lot like the Jensen Shannon divergence. So let's quickly discuss what the Jensen Shannon divergence is. It's basically a symmetric and smooth version of the KL divergence. So an important property of KL divergence, K dKL, PQ, right? This does not equal to dKL QP. These are not equal, and that would make sense because if you had done QP, then that would have been QXI times log QXI over PXI, and that's obviously not equal to what we have here, right? So these two things are not equal. So the Jensen Shannon divergence is just a symmetric version of it, and the way they write it is this. It's D Jensen Shannon of PQ is equal to, let's see here, 1/2 dKL QM plus 1/2 dKL Q, or not Q, it'll be P M, where M is equal to Q plus P over 2. So M is known as like the mixture distribution. There's a couple terms for it, but basically it's that. It's the average of your KL divergences between Q and the mixture distribution of Q and P, and the KL divergence of P and the mixture distribution of Q and P. So this is our Jensen Shannon divergence. And we can start to see some elements of this appear. We have here the sum of two different KL divergences. Well, we have here the sum of, or I guess not there, but here we have the sum of two different KL divergences, right? Because we saw that each of these are a KL divergence because it's like a expected value of the log ratio of something, which is exactly what a KL divergence looks like. And we're adding two of them together. So let's just start to kind of put some of these pieces in place. So what we're going to do is use our log rule, because we still have a little bit of work to go, like M here. So we have right now in the denominator PD plus PG. M should be PD plus PG over 2, right? So we're missing a 2 in the denominator. We're also missing a couple other things here and there. So we just have a little bit of manipulation to do. There's a couple ways you can do this, but we're going to do it the dumb and easy way so everyone can follow. So let's do the expectation of x from px. And now we have log, and it's going to be p data over p data plus pg, right? That's the first one. Plus the expectation of x from our generated distribution, and this is again going to be p generated over p data plus pg. That's our starting point from earlier, and there's a log on here as well. There we go. So that's our starting point from earlier. So we have a couple of log rules, right? So log of a over b is log a minus log b. We're just doing some algebraic manipulation now. So we're just going to rewrite some of this. So it's going to be the expectation of x px. And so the first term's going to be log pd, log of pd minus log of PD plus PG. PD plus PG. That's the first one. Plus the expectation, x coming from our generated distribution. And this is going to be log of PG minus log of PD plus PG. So there we go. That's the first step. Now, if we remember, we want our m to be the sum over 2. Okay, so we need that 2 in there somewhere. So let's just go ahead and introduce it. We want it to be PD plus PG over 2, right? So if we want to divide by 2, then we can also multiply by 2. And so what we can do is rewrite this as negative log, I'm not going to rewrite all of it, we'll just write this part. It's going to be 2 times PD plus PG over 2. Right? We're going to write this term like that. So if we multiply by 2 and divide by 2, that's no problem. And then similarly, we're going to rewrite u as log as of 2 times PD plus PG over 2, right? Doesn't break anything if we multiply and divide by 2. And then we kind of get this other thing here. Log of, again, remember log rules, log of AB is log A plus log B. So we can do that. We have log of 2 times this thing, and then log of 2 times this thing. So we can split this up. We can write this as negative log of 2 minus log of PD plus PG over 2. And then here we have negative log 2 minus log of PD plus PG over 2. Just like that. And so that's essentially the hard work already done. So we now have that ratio, right? The P plus Q over 2. This thing right here has now appeared. And so now let's just put it back in the correct form, right? We have a little bit of cleanup to do here. So remember, all of this stuff, right, is inside the expected value, and all of this stuff was inside the expected value. So that's still there. But log of 2 and log of 2, these are constants. So the expected value of a constant is just the constant. So we can actually just pull them out. And we have 2 of them, so we'll pull both of them out. So we'll have negative 2 log 2. And then we'll have plus the expected value of x, px. And what are we left with? We're going to be left with, let's do the first one. It's going to be the log of PD. We pulled this term out, so we'll have log of PD minus log of all this stuff here. And again, just going backwards from the rule earlier, log A minus log B is log A over B. So let's just put it back as a fraction. And so this is going to be log of PD, so it's going to be PD, divided by PD plus PG over 2. So PD plus PG over 2. So there we go. That's the first one. And then the second one, exactly the same setup. We have log of PG minus log of all this stuff here. And we already pulled this one out, right? That already came out. So we can do exactly the same thing. It's going to be plus the expected value, x coming from our generated distribution. And then we're going to have the log of PG divided by PD plus PG over 2. And now you should start to see exactly what's happening. This is just m, right? The sum of 2 things divided by 2 is m, is in the notation. So let's just plug that in. We're just going to write, instead of writing all this here, we're just going to say both of these are m. Where m, and we'll write m is equal to PD plus PG over 2. And also, this is the expectation of the log of a ratio. And that's exactly what our KL divergence was from earlier, right? So our KL divergence right here is the expectation of the log of a ratio. In this case, it's the ratio has a common m in the denominator. Okay, so that means this is negative 2 log 2 plus, this is the KL divergence of PD and m. And then the second one is going to be the KL divergence of PG and m. And again, m is just our mixture distribution, just like that. And so now that we have all of that, we have our last little bit of manipulation left. Because again, if we look at our Jensen Shannon formulation right here, there should be a 1/2 on each of these terms, which we're missing. And if we're missing a half, we can always just add it in. So it's going to be negative 2 log 2 plus, we can write 2 times, and then it'll be dkl pd m over 2 plus dkl pg m over 2. Right? This is fair. I multiplied by 2 and then divide by 2. And this is exactly our Jensen Shannon divergence. So we finally get negative 2 log 2 plus 2 times the Jensen Shannon divergence between our P, D, and PG. So this makes a lot of sense because our goal is to minimize this, right? And when we're minimizing it, this is just a constant, so it doesn't matter what it is. And so what we're really doing is minimizing the distance between our generated distribution and the true data distribution. And that's exactly what the generator tries to do. The generator is attempting to generate data that's so convincing that it's indistinguishable from the original data distribution. And so that's exactly what we have. So again, this is just a really cool aside to kind of see exactly what's going on more statistically, internally, that sort of stuff. But the key idea is this: our final loss function, our loss, is going to be, we want to minimize with respect to G. We want to maximize with respect to D. The expected value of X, Px of our log, of our discriminator of X. And then we'll have the expectation of X of our generated data. And actually, let's go back one more step just to make it look like the original kind of implementation. We'll say Z. Let's write it in terms of PZ again, the random noise distribution. And this will be in log 1 minus dg of Z. If we had written X with PG, then we would have just written X here, but this is fine. So this is our final loss function, what we're trying to do. In this case, we're minimizing with respect to G and maximizing with respect to D. And remember, this is again negative entropy, what the formula ended up being. So maximizing with respect to D is maximizing the log probabilities. We want our model, our discriminator, should be maximizing the probability and getting better and better at identifying which things are real and fake. And G is going to try to mess it up, right? It's going to try to go in the opposite direction by making the model, by making the discriminator unable to distinguish between them. And it's able to make it, well, I guess, yeah, it's able to make it unable to distinguish because the generator is effectively just minimizing the Jensen Shannon divergence between our true distribution and the generated distribution. So the smaller the distance between our true data distribution and our simulated generated distribution, the tougher time our discriminator is going to have to kind of pull them apart. And so that's it. I want to kind of cut it here. This was just a very quick run through of exactly what's going on in the GAN. In the next couple of videos, we're going to be implementing a simple version of a GAN, a conditional GAN. We'll be looking at, I believe, a DC GAN, a super resolution GAN, and we'll do some more fun stuff later that's not in my Git repo just yet, but I'm working on like style GAN, hi-fi GAN, and a bunch of other stuff. So I'll call it here. I will see y'all in the next one.